Hello everybody, welcome to Sky Guru. This is our second lecture in mathematics for CFD. In this lecture we'll focus on scalar, which is a rank 0 tensor. This lecture is presented by Dr. Aishwarya Kumar. I'm a PhD in mechanical engineering from City St. George's, University of London, and I work for Sky Guru, which is a unit of Sexbury. So we will talk about scalars. What is scalar? Scalar has only magnitude. It has no direction. Examples include pressure, temperature, intensity. The main idea is that at every point of space, it has only one numerical value. So in the previous lecture, we also discussed that scalar is a rank 0 tensor. I mean, if you look at the tensor classification, the rank 0 tensor is a scalar, the rank 1 tensor is a vector, and the rank 2 tensor is a tensor, like a stress tensor. So, I mean, if you look at the mathematical meaning of rank 0 tensor, it simply means that, scalar is always a real number. Phi is always a real number. So it has no indices, no components, no direction. Let us try to understand the scalar field. So scalar has a value at every point in space. Like here I have written phi equal to phi as a function of x, y and z, because phi varies locally in the space, and it is called a scalar field. For example, pressure, which is also a function of x, y, z, varies locally. Temperature also varies locally, and density also varies locally. Hence, at each point in space, the scalar has one and only value. It has no direction. That's why it's called a scalar field. So let us look at the hydrostatic pressure example. And so hydrostatic relation says P equal to rho GH, where let us assume that density and the gravitational vector remains constant, then pressure varies with height. So let us assume that depth varies only with the vertical coordinate y. So as the magnitude of the y increases, where it shows h equal to minus y, so as the magnitude of the y increases negatively, the magnitude of the pressure increases. Then the pressure fields becomes P, which is function of x, y and z, equal to rho g times minus y. So there we can say that pressure increases with depth, and when we observe it, like if you look at an example of a pond or a swimming pool, then we can say that at the horizontal level, the magnitude of the pressure is always the same. Now what we'll do, we'll try to visualize the scalar field. We will again use the hydrostatic pressure example. P equal to rho GH. We are assuming that fluid is at rest and the free surface at y equal to 0, which means that the top of the surface is exposed to the atmosphere, and the depth increases as we move downwards. And the objective of the next slide will be to see how scalar field varies in space. We'll be writing a Python program to do it. So let us try to work on Python now. I'm minimizing this and opening the Visual Studio Code and starting with a new file, Python file. We can say 5 save as, and we can call it hydrostatic pressure, and we'll try to visualize the hydrostatic pressure using Python code. So let us import libraries. Let us define physical parameter. Let us create a 2D space. So y varies from 0 to -5 because it increases negatively because it is a depth. So what we'll do, we'll try to create a grid now. Now what we'll do, we'll try to plot it just to see the grid. This is to ensure that we have perfect square grid. Let's try to look at the grid now. Let's run the program. Let's hope it works. Now we have to run it again. Let us do it again. I'll have to check it. Why it is not showing? Give me a moment. Sorry guys, I realized my mistake. I had to put brackets here and now it will show. So now we can look at the computational grid. It has like 10 division in X direction and 10 division in Y direction. And now what we'll do, I believe this grid is too dense for the problem, so I'll try to refine it. So I'll increase the number of division in x and y coordinates. So I'll just, from 10 I'll make it 100, and from here I'll do the same and just try to run the program again. And now it looks pretty dense now. So now we'll try to define the function. Write a program function for a hydrostatic pressure field. Let's try to plot it. So I will not be doing the same mistake again, and let's try to run the program. So now we are visualizing the pressure field first, sorry, the grid first, and then we'll visualize the hydrostatic pressure field. Now here we can look at the hydrostatic pressure field. We can see that we have successfully generated the two-dimensional contours, and we can see that pressure increases as we go towards the depth, and it doesn't vary in x direction. So at the level it has the same value, like at -5 it has the same value, at -4 it has the same value, at -3 it has the same value. But as we go towards the bottom from the top, the value of the pressure increases. So we have successfully managed to visualize the pressure field using the Python code. I would like you to what I'll be doing, I'll be cancelling it out or maybe minimizing it and show you the program so that you can copy it and try to do it on your computers, so that you will also learn how to do this process. So please have a look at it for 10 seconds or maybe pause the video. So now I'm minimizing this and opening the slides again. So I would like to say thank you for watching this tutorial and spending your time on it. If you want any technical assistance regarding mechanical design, engineering and simulation, you can contact us using the email info@skyguru.in or using our alternative email address indiaskyguru@gmail.com. You can also WhatsApp us on +91 983 983 9753. And if you found this lecture helpful, please consider liking it and subscribing to our channel to support us. Thank you very much.